Hello, everyone. Thanks for joining us today for our AMS webinars, the latest edition in our AMS webinar series. This one is titled Hole Machining in 2 and 3-axis CAM. And my name is Joe Anand. I'm the product manager here for our CAM products in Microsoft. I'll be joined today by Uday Honalagare, our support manager, who will be actually doing the demonstration and showing you the different aspects of hole machining. And yeah, we want to keep this interactive, and we would like to, as the webinar progresses, if you have any questions, you can use the chat window to type in your questions, and I'll be in the background monitoring the chat window for any questions, and I will do my best to answer them. And if we need to stop with it on the demonstration, and if there's anything that you need additional clarifications, we can always show you that. And as always, the recordings of this webinar will be made available after the webinar. It'll take us a couple of days to clean it up, and we'll send it out to the registrant list. And also, we want to keep it interactive, but also at the same time, we can leave some time at the end if we have time. Actually, most of the time, the webinars seem to be running. We seem to be running out of time, but we like to keep the last 10 minutes for questions, if possible. I will try to do that again in this webinar. Today's webinar is titled Hole Machining in 2 and 3-axis CAM. The topics that we're going to be covering today, the first topic would be hole selection techniques. Uday is going to be showing you the different ways we can select holes and actual selection of these holes for machining. This will be followed by the hole cycles operations, or the hole machining operations themselves, like parameters. We'll be describing each of the parameters, not most of the parameters anyway, most of the important ones. And I'll follow it up with the description of the milling operation parameters, and how to use them to control your hole machining or hole milling. And then also you'll be talking about automation of hole machining. This is an interesting area where there are many tools in the system that will allow you to automate hole machining, and he'll spend quite some time on that. And then finally, some of the output control features in the product, as well as some post-processor options that you can use to control your output. So without any further ado, Uday, go ahead and take it up from here.
Thank you, Joe. Hello, everyone. Good morning, good afternoon, or good evening to you all, folks. And thank you for joining us for today's AMS webinar series on hole machining. I will be covering the different aspects of hole machining in our Microsoft CAM products. And at any point during the webinar, if you do have any questions, please feel free to post those questions in the questions panel, and we'll try to get those questions answered to you. Now, first, I would like to start with the hole selection techniques in here. And we will start with our standalone product, which will be Visual CAD/CAM, and then we will look at RhinoCam and Visual CAM for SolidWorks as well. The workflow would be very similar, whether you're running Visual CAD/CAM standalone or RhinoCam or Visual CAM for SolidWorks. So we want to get through all the different features types in here that you can use for hole selections in here. So hole selections can be performed for it if you're working off of like a 2D drawing, if you're importing like a DXF, DWG file, or if you have some sketches that you're working with. It's just 2D. There's no solid surface model, provided to you by your customer, or if you designed it just as a 2D, you can take advantage of those 2D geometries in your hole selection techniques. So there's two types of hole machining operations. One is the cycle types, which could be like drill, tap, bore, reverse bore, and then we have hole pocketing and hole profiling as the hole milling operation types. So first we'll be focusing on the hole selection, and then we'll take a look at the different parameters like the cycle parameters and the milling parameters in here. Now, what I have here is a 2D drawing here. It was just either drawn in Visual CAD or imported into Visual CAD. And one of the ways that we can go about selecting these holes for machining is under hole machining operations. If you select drill, you have different ways you can select holes. You can do select drill points or circles. So you can actually just pick even a point as the location of your drill or it could be even used as the location for where you want to do a pocket, whole pocket, or a whole profile. So we'll look at select drill points and circles. You can interactively select these points by just picking them on your graphic screen, or you can drag a window to select all of them, or you could even use the tools, the selection tools that are available to you in the CAD section, where you have modeling aid and you can say select points. It'll automatically pick all the points that are visible in the current layer or in the drawing. So if you have multiple layers, it'll pick all points from all of the layers that are visible to you. So once you make the selection, right click, and you can see that the 3 points that you selected are automatically added to the list. And the next step is you make a selection for the tool, you specify your cutting parameters, and generate the tool path for it. Now, one of the other ways for selecting holes is by selecting arcs or circles. So in this particular example, we have a number of holes, circles of different sizes in here. So I could go into hole machining and select drill, and I would like to select circles of a certain size. I'm going to use select drill points and circles, and I'll just drag a window to select all of these geometries in here, and I can apply a range filter. I can select use diameter range filter, and I can specify the minimum diameter and a maximum diameter. So in this particular example, I'm going to pick a maximum diameter to be one of these smaller holes. Now, once I pick a maximum diameter, you see that once I select an arc or a circle, it automatically establishes the maximum diameter. So it determines what the diameter is, and it drops the other holes that were selected. So the filter automatically limits the hole sizes in here. So once you made the selections for the hole size, you could go into your tool tab to make a selection of the tool. So I have an entire library of tool listed. So I'm going to pick a 3/4 inch drill, set the feeds and speeds, establish clearance, cutting parameters, the depth of the hole, and then generate. So now the tool path has been generated for the holes of 3/4 inch diameter. Now, one of the things I would like to point out here is you can see that the holes are drilled in a random order, and we will talk about how we can go ahead and sort them so it'll minimize the number of transfers and make it much more efficient. And then we will do that when we cover the whole cycle parameters. So we looked at how we can select points for hole machining. We looked at how we can select arcs and circles. So in this particular example, we only have circles. So you can select circles, and you can apply diameter filters to select circles of a certain size. Now I'm going to repeat the same operation again. I'll do a copy paste. You can do Control C, Control V, or you can do right click copy and right click paste to make a copy of it. I'm going to edit this operation again, remove my selections, go to select drill points and circles, drag a window to select them all again. And now for the diameter filter, I'm going to set a minimum diameter to be the size of this particular hole. So you'll notice that now only the larger holes are selected in here, and then I can specify a tool that's appropriate for it. Now there isn't an 1.5-inch drill, so I'm going to pick the largest drill size that's available in here, generate a tool path for it, and then I can go ahead and use a whole pocket or a whole profile operation to basically mill it to the size of the exact size of the hole. So if you do not have a tool that matches the diameter of the hole, you can actually use a whole pocket or a hole profiling, and this can be found under 2-axis machining methods. And we'll cover that during the later part of the webinar, the different types of milling, hole milling methods as well. So in this example, we looked at how we can select points, select arcs and circles. This is one of the options for hole selection. Now the next example I'm going to go over is how we can select face edges, flat areas when you're working with solid surface geometries in here. Now for this, I will switch over to an example in CAM, and we'll cover that. Now the workflow remains the same whether you're running CAM, Visual CAD/CAM, or Visual CAM for SolidWorks. Now the example I have here is a solid model, and you can see there are different hole types in here. You have through holes, you have counter bores in here, so there's different types of holes, and there aren't any curves or sketch geometries on the model. Now you can extract those curves or sketches from the model using the curve extraction tools available in the CAD system. If it's Visual CAD/CAM, you can use flat area regions to extract them. In RhinoCam, you can use what's called duplicate face border that's available under curve from objects, duplicate face border. You can use these tools in here to extract the curves from the model using duplicate face border. Now, the alternative way is you don't have to extract those curves or edges from the model. You can directly select face edges or surface edges from the 3D model. So I'm going to go into hole machining and I'll pick drilling. And now I can select drill points and circles again. And I can pick the face edges from the model. I can just go pick the surface edges. I can either pick an arc or I can pick the entire face edge, which is split up into 2 arcs in here. So I can select these 2 and then right click to accept my selections. You can see the 6 face edges have been selected. And as you highlight them in the selected holes feature list, the corresponding face edges are highlighted on the model as you see it. In the next step, you make a selection for the tool. I'll pick a 1/4 inch drill bit in here, set feeds and speeds, clearance, and we can also pick the depth off of a 3D model as well. And then generate, create your toolpath. So we've selected face edges in here as machining regions. Now we can also select face edges from partial holes. I've just made a copy of the same operation. I'm going to edit, select remove all, click on select drill points and circles, and I can select these partial arcs. Right click, generate. So we could select face edges, we could select points, and we could select arcs or circles, which could be 2D geometries. Now the next selection technique we'll cover here is using flat area selection filters. So as we go into hole machining and drilling, the second choice here is select holes on a flat area. So select holes on a flat area will prompt you to select a flat area. So basically you want to pick a planar face. You could be working with a solid surface or a mesh geometry. So the flat area selections work with solid surfaces and mesh geometry. So when you select a pick a flat face and then right click on it, it automatically identifies all of the holes on the flat area that you picked. And you can apply a diameter filter in here, and you can specify to ignore holes that are larger than a certain size, like a 1/2 inch in diameter. You can specify a filter in here and it'll exclude holes that are larger than 1/2 inch or whatever size that you put in. In this case, we probably have holes that are larger than 0.4 inches are excluded. You pick your tool and then generate, create your toolpath. Now the face edge selection that we talked about just a moment ago will only work with solid and surface geometries. The face edge selection will not work on mesh geometries. So for mesh geometries, you'd either have to use flat area regions, holes on flat area, or you'd have to create curves from the mesh geometry and pick those as select drill points and circles. So the face edge selection works with solids and surface geometries only. Now we looked at the flat area selections. Now there's one other way how we can select flat areas is by the use of predefined regions. Now the predefined regions would have to be first created before they can be selected. So as you can see here, the predefined region list currently is empty because we have not created any predefined regions. So to create predefined regions, we will have to go into the machining objects browser. So if your machining objects browser is not visible, you can toggle it by selecting tools, machining objects, and then you would want to go over to the regions tab, which is right next to the tools tab on the machining objects browser, and you can use what is called select flat areas. That's one of the ways to create predefined regions. using select flat areas, and I can pick a face and then right click will create regions around each hole, and each of the regions have been separated out. So as you select the region set, you will see there's regions created for each hole. You can also apply filters for the flat area regions, so to identify the type of regions you want to extract. So in this example, I only chose to extract holes, just arcs and circles from the model. So I chose not to extract the outermost region. So I had the ignore outermost region selected. So this is one of the ways how you can create predefined region. You can also create predefined region using surface edges. So I can use select surface edge areas, and I can pick these edges in here and create a predefined region. So we have predefined region created using surface edges. We could create predefined region using curves as well as flat area regions. Now, once we have these predefined regions created in here, you can go into your machining operation and click on select predefined, and you'll now notice that the two predefined region sets are displayed. And if I would like to drill all of the holes, let's say I would like to do a pre-drill operation for all the holes, I can just highlight the region set and it'll automatically select all of the regions that are in the region set to the selected hole features. You then specify your tool, specify a cut depth in here, and then create your toolpath. So we talked about drill point circles using points, circles, face edges, flat areas, and predefined regions. The next thing I'm going to cover is how we can use features from model to program hole features. And I'll take an example for that here. Now here I have a solid geometry, and under the features tab, we have automatic feature detection. So when you run an automatic feature detection, different feature types are identified from the model. So in this webinar, we'll be focusing on hole features. So you will see that there's 3 different types of hole features that have been identified. And as you hover and select one of the features, it gives you information about the depth and the min and the max diameter for each of the features that were identified. So if you're working with solid surface geometries and you have prismatic parts, you could take advantage of feature detection. And once you have these features detected, you can automatically do what is called feature machining. So in this particular step, it automatically selects those features and creates the machining operations. And you can edit the operation to pick a tool that's most appropriate in here. And you'll also notice that the tools are automatically filtered out based on the diameter of the feature, the hole feature that you selected. So in this case, we have a 3/8 inch hole. So I can go ahead and select a 3/8 inch drill and generate the toolpath for it. Likewise, I can do the same thing for the 2 1/4 inch. Pick a larger tool in here and then generate a toolpath for it. So just to summarize what we covered so far is the different selection techniques using points, arcs, circles, using face edges, flat areas from solid surface mesh geometries, predefined regions from solid surface mesh geometries, and predefined regions can be created using curves, face edges, as well as flat areas. The next thing we would like to cover today is the whole cycle operation parameters. And I will go with that starting with this example in here. So we have created a drill operation. Now the whole cycle operations, we have different types of whole cycle operations. We have drill, tap, bore, and reverse bore operations. And under drilling, we have different operation types. We have standard drill, where you drill to the total depth in one go. You have deep drill, where you basically pick and retract and you can specify by specifying step increments. So as you select deep drill, you can specify your step increments or depth per peck. We have countersunk drill operations, where you can specify the countersunk diameter and the depth is automatically determined. We have break chip cycle. Break chip drill is similar to deep drill, whereas the retract only goes up to the previous step increment and not all the way back to the clearance plane. So the difference between break chip and deep drill is where the break chip only retracts to the previous cut level. And then you also have user-defined drill cycles, where you can have a custom drill cycle being output in the post, and you can specify the cycle parameters. So as you select one of these drill operations, so let's say we want to pick a deep drill operation in here. The depth, since in this particular case we're using feature-based machining, the depth is automatically determined from the hole feature. You can see the depth is determined here. It's 1 inch in depth. Now we can specify the option to add tool tip to drill depth. So this will ensure that the tip angle of the tool that you define will go past to clear past the entire depth, so it makes it a through hole. If this is not checked, you can see in the tooltip help that pops up here with the difference between add tooltip to drill depth being unchecked versus checked. So it'll not be able to make it a through hole if you do not have the add tooltip to drill depth check. Now, if you'd like to dwell, like leave the tool in the hole for a few seconds, milliseconds, you can use the dwell options. The approach distance can be used to basically specify the distance above which you want it to retract the reference plane before it starts applying your cycle feed rate for drilling. Then finally, if you want to apply some sort of a sorting, not have the holes drilled in a random order, you can choose sorting. Either you can apply minimum distance sorting, so you can sort them based on minimum distance between 2 or more holes, or you can even apply directional sort. So this will make the sequence of hole drilling much more efficient by applying a sorting sequence in here. Now let's go ahead and apply the same to one of the other parts we worked on earlier. So I'm going to go back into this standard drill operation on the 2D drawing. We'll apply sorting, and I'm going to choose minimum distance, and I'll say starting from the lower left corner, which would be the corner that's closest to the origin, and then pick generate. So you'll see that the sequence is much more efficient here, so making less number of transfers and reducing the number of transfers between each hole. So you can apply sorting in all of the hole machining operations. Now we're going to take a look at an example where we can do some tapping operations as well. And let me go ahead and pull in a file for that, and we can cover some tapping operations in here. Folks, again, if you do have any questions, please feel free to go ahead and post those questions in the questions panel, and we'll get them answered for you. So typically on a hole, you would want to do like a spot drill, which could be started out with a drilling operation. It could be a standard drill operation. You can specify a depth, just spot drill it to a depth of like 50 thousandths. And then you want to drill all the way through to the total depth. So in this case, we're going down to a depth of 1/4 of an inch. And then next thing you want to do is tap. So if you need to, the holes need to be tapped, you can select hole machining and tapping under the hole machining operations. And you can select a tool for tapping. So in this example, I'm going to pick a 1/4-20 tap, and you can specify the tool diameter, your thread pitch, and then make sure to set your spindle RPM in here. Now the feed rate for tap, I'll cover that when we get into post-processing. There's different ways how the feed rate for tap can be established, and we'll go over that. As far as the cutting parameter goes, the parameters tab interface looks very similar to our standard drill operation, where you can specify or select the type of tap. You can do just a standard tap, or you can even do like a peck tapping by specifying a peck depth per peck, like a step increment, and specify your total tap depth and the approach distance, which is basically the the retract plane until which the tool will wrap it down to the approach distance, and then it'll apply the cycle feed rate for the tapping operation. And you can pick the tap direction and apply sorting to the tapping operation. So I've already created a tapping operation in here. So we have a drill, spot drill, drill, and a tap operation. In all of these three operations, I have grouped them into what is called a machining operation set. So you can create a machining operation set under miscellaneous operations. You can add a machining operation set, and you can drag one or more operations into the machining operation set to group them into a machining operation set. So if you're going to be doing a spot drill, drill, and a tap for the holes of the same size, it would be a good idea to basically go ahead and put them in a machining operation set, and we'll show you how we can automate the process of selection of the holes for drilling and tapping in the later part of the webinar today. So once you have these programmed, we have a quarter 20 hole. We also have a hole program for a half 13. You can take all of these and then save them into a knowledge base. You can probably refer to one of the past webinars on how we can save the operations to a knowledge base. So select the operations, save them out to a knowledge base. So these are the different types of hole machining, CAN cycle operations like drilling, tapping, bore, and reverse bore. They're very similar to like drilling and tapping, the bore and reverse bore. The cycle types are different, like a bore could be a G85 through G89. A drill operation could be G81, G82, G83 for a deep drill, G84 for a tap cycle. So these are cycle operations. Now we also have what are called a hole milling operations in here, and we'll go through an example for that for a hole milling operations. Now you could have certain holes that are larger in diameter. For example, if you take a look at this one here, you have these large holes on the model in here. So these holes you may have to drill, and then you need to clear the material inside those holes. So for those, you'd have to program them using either hole pocketing or hole profiling operation. So once you have drilled those holes, so in this particular example, I'm going to go ahead and first drill these holes in here, and I'll pick a tool for drilling it. So I'll go pick this tool, and I'll leave the depth as a 1/8 of an inch. That's the depth of the hole. I'm going to click generate. So we have the hole drilled in here. Let's run a simulation. So you can see that the hole is drilled, and we would like to go ahead and remove the other material around to bring it to the hole size. One of the techniques you could use is an operation called hole profiling. So hole profiling considers that you already roughed out the hole, and you can basically do a finish operation to bring it to the exact size of the hole. So you can use select curve edge regions for hole profiling. I can either pick an arc, or I can pick both the face edges, make a selection for the tool. So I'll go pick a 1/4 inch end mill for that, set the feeds and speeds and clearance. Now under cutting parameters, you have different options in here. So the location of geometry, you can set it to be at the top, since the feature what you selected is at the top face of the hole. You'll leave it at the top. The hole depth, you can pick the depth from the model. That's an 1/8 of an inch. Or you can even say determine depth using 3D model. Now for the hole diameter, by default, for arcs, use arc diameter is checked. This means the system automatically figures out the diameter of the arc that you selected in here. If you'd like the hole to be oversized, or if you chose a point as your machining region, then you can clear this checkbox and you can specify the diameter of the hole. So if you picked a point, or if you'd like the hole to be either oversized or undersized, so you don't have to go back and redraw the part, you can change the diameter right in here, and it'll go basically mill it to that particular diameter. So for this example, I'm going to say for arcs, use arc diameter, and then you can specify the parameters like your helix pitch, and you can set the parameters for creating full 360 helixes and outputting each helixes individually if that's what your controller expects. And if you're doing multiple holes, you can apply sorting, very similar to how we applied sorting in the drilling operations. So selecting generate creates a hole profiling operation. And I'm going to go ahead and run a simulation in here. Now, if you'd like to use a smaller tool to program an entire hole, rather than doing a drilling and a hole profiling operation, we could use what is called hole pocketing. And this can be used for holes of any size, as long as you're going to be using a tool that's smaller than the diameter of the hole. And then you want to pick a tool, so I'll go pick an 1/8" tool, set my feeds and speeds and clearance. So I'm going to let the feeds and speeds automatically load from the tool. In the cutting parameters, you can specify the location of the cut geometry, the hole depth. So I'll pick the depth. And for the diameter, I've set it to use arc diameter, so the system automatically establishes the diameter of the hole. And since this is a hole pocketing operation, so you have 3 different types of cycles. You have a helical interpolation, a spiral, and then a final cleanup pass in here. So we have a cleanup pass selected, and you can specify the number of levels for the cleanup pass. I'm going to pick 2 levels, specify the step over control for the spiral cut pattern, and then in the entry and exit tab, I will be specifying the helix parameters. The helix diameter can be set right in here, the helix pitch, and you can apply the full 360 helixes and output each helix individually. So selecting generate creates a hole pocketing operation, and as you can see here, it starts out with a helical pattern. There's a spiral to basically get to the diameter of the hole, and then a final cleanup pass at each level. So since we set the number of levels to 2, so you have these being applied at each level. So as you run a simulation, you'll see that it starts with a helical path, then a spiral, and then a final cleanup pass. Now each of these can be output as scan cycles, or it can be linearized. We'll talk about that in the output control and post-processing step. So these are the 2 types of hole milling operations that you can apply: hole pocketing and hole profiling operations, in addition to the hole machining cycle operations, which could be drill, tap, bore, and reverse bore operations. Folks, if you have any questions, please feel free to post those questions in the questions panel, and we'll try to get them answered for you. The next thing we would like to cover here is hole feature detection and machining, and we'll also talk about automation of hole machining. So for hole feature detection and machining, I'm going to use the same example that we have in here. I'm going to go over to this features tab, and I'll choose automatic feature detection. Now the automatic feature detection is available in all configurations starting with standards. If you're running standard, expert, professional, or premium, you will see the automatic feature detection. This is available in Visual CAD/CAM, RhinoCam, as well as in Visual CAM for SolidWorks. So when you click on automatic feature detection, the system automatically analyzes the part and identifies all of the different features in here. Now in today's webinar, we're going to be primarily focusing on hole features. And as you can tell here, there's different types of hole features identified on this particular part. We have hole features identified even for partial holes. I have a filter that can select only enable the partial holes also to be selected. So we have the partial holes selected. We have hole features detected for through holes, hole features for like counter bores. So you have hole features identified for each and every hole type that can be found on a model. So there's basically 5 different types of hole features. Now if you just individually like to program each of the features, you can select them, right click on it, and you can choose the type of operation you would like to apply. I can choose drilling, and this automatically has all of the features selected for the features that have the same hole, exact same hole cross section. So in this particular example here, you can see that the diameter of the hole is 0.112. So it automatically selects all of the holes that are of 0.112 diameter, and they're automatically grouped as instances under each hole feature when there is a hole feature of the exact same cross section. The next step is to make a selection for the tool, and you'll notice that there's a list for filtered and a full list. So filtered automatically lists only holes that are equal to and less than the diameter of the hole feature cross section that's been determined in here. So if you go to the tools tab, you will notice that the closest tool I can pick is drill number 34, which is 0.111, or I can go maybe to 0.113 if you want the hole to be slightly larger. So I can pick one of these two from the standard drill tool list here, and you can specify your parameters. Now I don't have to specify any depth. All I'm going to do is add tooltip to drill depth and apply a sorting to it, and then pick generate. So we will automatically be able to generate tool paths for the hole features. Likewise, I can apply hole features for the other operations too. So you can program each of these hole features, and one of the nice things you can do is you can save them into a knowledge base, the hole features, and if you have other parts that have similar cross sections for through holes or for counterbore, you can program them, and I'll cover that in another example in here. So we'll take a look at another example where we're going to be programming hole features. So in this particular example, we have three different types of hole features. We have through hole. We also have a counterbore in here. So I'm going to select the counterbore, right click on it, and I'm going to choose create hole feature machining knowledge base. You can either access this from the right click menu, or you can access it by selecting it from the features tab on the toolbar right below the features tab. Now you can see that the feature cross section is displayed in here. Since this requires more than one operation to program this entire hole cross section, I could start out with a standard drill, and then when I select the standard drill, I can change and modify the depth, how deep you want it to go. I can adjust this in here. For example, I could say I only want to drill 75 thousandths deep on the standard drill, which could be like a spot drill operation. And then I can do a deep drill operation, drag and drop it, and I want to go all the way through for the deep drill. And finally, I would like to use like a hole profile or a hole pocket to mill the hole on the top. So I'm going to select the hole profile, and again adjust set the depth in here. So the depth is automatically being set right there. Now once you have these created, you can save them into the automatic feature machining knowledge base, or you could just create them as a hole feature machining operation set in here, and you can go back and update the tool to match the tool for the hole size. In this case, I would like to use a 1/2 inch tool. So I'm going to pick a 1/2 inch drill for that, and then specify any additional parameters like sorting, generate it, apply the same workflow for a deep drill operation in here, add the tooltip to drill depth, apply the sorting, generate it, and finally on the hole profiling operation, I see that the hole diameter is 3/4 of an inch, so I want to pick a tool that's less than that and specify all the cutting conditions in here, specify your parameters, choose your cut direction, and you can apply the sorting, generate it. So once you have these generated in here, you can right click and save this out to a knowledge base, and you can put it under the feature based machining knowledge base folder. And the feature based knowledge base folder can be found under program data, Mexsoft, and the product that you're running. It could be Visual Cam 2019, Rhino Cam 2019 for Rhino 5 or 6, or Visual Cam for SolidWorks under feature based machining, and you want to save it under this folder. Now by doing this, one of the benefits is if you happen to have another file that you'd like to program, so let's say you wanted to go back into the file that we worked on earlier, I can just select one of these hole features in here, right click on it, and I can say automatic feature machining using the knowledge base. I'll pick the knowledge base and then select generate. You'll see that it automatically created the standard drill operation for the spot drilling, the deep drill for the through drilling, and then the hole profiling, because it found an exact match for the same cross section, except the diameter, the depth were different, but it found an exact match for the same cross section. So you can automate your workflow, and all you have to do is go back and pick the tool that's the most appropriate for this hole. So it's going to be 0.112, so I'll pick this, generated. So that's all I'm having to do here is go back and update the tool for it, and the depth, the sorting parameters, all of the information is obtained from the knowledge base in here, and I can select the tool as well that's most appropriate for it. So as you can see, the sorting sequence, all of it is automatically, pulled from the knowledge base. So by this, you can automate your workflow when you're working with whole feature machining operations. Now, the next automation I'm going to talk about here is how we can automate by applying selection rules when we are working with, curve geometries for programming holes. Now, in order to demonstrate that, I'm going to go ahead and go back to this example in here. And as you notice in this particular example, we programmed a drill and a tap operation for each of these holes, and we grouped them under what is called a machining operation set. And we saved it to a knowledge base. Now, in order to apply rules, I'm going to go to this knowledge bases tab and load that knowledge base, which I created. It's called drill and tap. And you can see that in the K-Bases tab, you now see a new item called selection rules. And I'm going to double click on it. And I can apply the selection rules using either a geometry filter, a layer, or a color filter to select those objects. So in this case, it'll be able to select curves, drill points based on geometry type, layer, or color filters. You can apply them. So for the quarter 20 hole, I could say pick circles of a diameter from 0.24 to 0.26 inches, and then apply it. And I could do the same thing for the half-an-inch holes, pick the circles automatically of a size 0.5 to, I'll put in 0.55 and apply it. So now we've set up the rules, so it'll automatically apply the rules for all the operations that are inside or within a mop set. You could then save this out as a knowledge base. I'm going to go ahead and save this out in here. And let me go ahead and program another part. So I'm going to go ahead and open this fixture plate. And you'll see that we have holes of different sizes. Now, to be able to automatically program this, I'm going to go to knowledge base, load knowledge base. I'll pick the knowledge base which I just created with the rules. And you'll notice that the regions were automatically selected. So if I select the operation, you can see the spot drill, standard drill, and tap automatically were selected based on the selection rules we put in. And for the half 13 as well. So all I have to do is right click and regenerate. Now the part is ready programmed. I can run a simulation. And it's ready to be post-processed. So with the selection rules, you can automate your programming workflow. You can also use the feature-based automatic feature machining knowledge bases as well to automate your programming workflow in here. So we talked about two different ways how we can automate it. So the next thing we will be covering is the output control and the post-processing options. Before I do that, I did forget about one topic I wanted to cover here, is how we can use drill points and have those drill points projected to 3D model. So I have an example here, and you can see what I have here is a sculpted surface. And I have a bunch of points that I've created on it. So the points are all planar, as you can see. And I would like to drill holes and have those projected to the 3D model. So you can use select drill points and circles to select all of these points, or you can use the selection techniques that are available using select by layer, select by color, select by type in Visual CAD, CAM, and Rhino. And then in the cutting parameters, you see under location of drill points, you have this option that says project to 3D model. So these points are automatically projected to 3D model. And then if you set a depth of 150 thousandths, the depth is determined from the point at which it projects it down. So it'll go 150 thousandths down into the model based on the projection points. And then you can apply your sorting and generate the path. So now I'm going to go ahead and run a simulation in here. I've defined a stock using stock from selection, or you could even have it roughed and finished out to the shape of the part. And then I'll run a simulation in here. You will notice that the tool path is being projected to the model. The points are projected to the model, and the depth is determined from the point where it's projected to. So if you have a pattern that you're trying to create, this might be a very easy way to program it using a drill operation. And you can always speed up the simulation using the simulation controls. So I'm going to choose pause and then pick simulate to end. So you can see that the points are projected and the depth is determined from the point where it's projected from. Now let's take a look at the output control and the post-processing options. Now you will find these under CAM preferences and machining. First, we'll talk about the drilling. Now by default, always output as linear motions is not selected, which means you will be outputting them as canned cycles. So canned cycles are G81 through G89 for drilling operations. So if I go ahead and post-process this operation, and I can pick a post from the list, I'll just pick the FANUC post processor, and you'll notice that the output has a can cycle, a drill cycle for each of the holes. A G81 represents a standard drill cycle. Now if you change this from a standard drill to a standard drill, if you apply a dwell on it here, you generate it and you post it, it'll be outputting as a G82, which is a standard drill with dwell, and you can see the dwell is output as a P, and a 5 could be 5 milliseconds or 5 seconds depending on how the controller interprets it. So these are output as can cycles. Now let's go into an example where we have a tap operation in here. So I'm going to right click and do a post, and I'll pick a post for this. Let's say I want to pick a post processor, and then select post. You see you have a G81 for the drill, and then you have a G84 for your tap operations, which is a clockwise tap. So these are output as can cycles. Now if you go into CAM preferences machining and select always output as linear motions, now these would be output as simulated cycles, which means they would be output as a G0 or a G1 motion for standard drill, deep drill, countersunk, brake chip cycles. Now this would not apply to tap cycles. You will not be able to output a tap operation as a linear motion or simulated cycles. This would only apply to the hole making like standard drill, deep drill, brake chip, and countersunk. The tap cycles would still continue to be output as, G84, which is a cycle. So as you can see the difference here, we are no longer seeing a can cycle. It's being output as, a G0 rapid move to position the location of the hole, and it goes at a linear motion with the programmed cut feed rate to the depth of the hole. So that's your output control to output either as a linear or as a can cycle. Now when outputting as a can cycle, there's one option I would like to point out here is as you post-process the machining operations, you will notice that the G81 line is output for each and every hole that's being drilled. So if you have 10 holes, you'll have 10 G81s being output. Now, one of the nice options you have in the post is to optimize the output, which repeats the G81 only on the first hole, and then it'll just output the subsequent X and Y motions. You can select optimize cycle output, and then when you go back and post process the toolpath again, you will notice that only on the first hole you're getting the CAN cycle, and then for the subsequent holes you're just seeing the X and Y coordinate values being output, and then the cycle is canceled to G80. Now this applies to all CAN cycles, drill, deep drill, and tap operations as well. If you're outputting as CAN cycles, you can do an optimized cycle output. Now the next thing I'm going to cover here is the cycle options, the feed rate options for tap cycle. So typically a tapping operation for a feed rate for tapping operation, most controllers prefers the tap feed rate to be output as pitch times RPM. So if you go into the help section and under tapping, if you click on tapping feed rates, you see that the different ways how you can output the feed rates. The most common is cycle IPR, which is spindle speed that you define in the machining operation, times the thread pitch that you define with the tapping tool. So if I go into the feeds and speeds tab, you'll see that the spindle speed is set to 500 RPM. And as you look at the tool definition, you have your thread pitch set to 50 thousandths. So the feed rate is automatically computed using pitch times RPM. And as you take a look at your posted code, you will see that the pitch is output. The feed rate is output as pitch times RPM, which happens to be 25. Now, if you're expecting the pitch to be output as just the thread pitch that you put in, you can change it to cycle underscore TPI or 1 over TPI, or if you want to output the feed rate that you programmed, defined in the feeds and speeds, you can use the cut feed variable in here. And this can be set in your post processor under cycles for tapping, and you can swap this variable out with the variable that's most appropriate for your machine controller. You can right click to pull in the variable list, and you can swap it out with the variable that you'd like to use. Now the last thing I'm going to cover here is the CAN cycle options on milling operations, which are hole profiling and hole pocketing. So on a hole profiling and hole pocketing operation, you have the option to output the helical interpolations as either as linear motions or as helical interpolations, and this can be set under CAM preferences and machining, and you have these options. So by default, output spiral motions as linear and helix are checked. You can clear this checkbox for helix motions as linear segments, apply it, and make sure to regenerate your machining operation before you post it. So right click and post, and when you post the output, you'll notice that the helical interpolation is output using GO2 or GO3 with X, Y, Z, I, and J. So there's your helical interpolation for the hole profiling operation. So if your controller supports helical interpolation, you'd want to select that. If your controller supports spiral interpolation, you want to select it. And also you need to make sure that your post processor is configured for both helical and spiral interpolation. So on this particular post, you can see that the controller only supports helical but not spiral, so the post is not set up for spiral interpolation. So you want to make sure that you choose output as linear motion for spiral interpolation and have these two unchecked. So now when we go back and repost an operation, so in this case I'm posting a hole pocketing, you'll see that the spiral interpolation is being output as a bunch of linear motions, and then you have your helical interpolation, and finally the cleanup pass as a circular interpolation at the very end. So these are the different output control options that are available to you for CAN cycles as well as in hole milling operations.